Hey guys, in this video, I want to find the connectivity of the following graph G. We're going to make use of the previous result in question 6. Let me recall this over here, which says that if a graph G is K connected, then the graph, which is obtained by adding a new vertex Y with at least K neighbors in G, will be K connected. So we are going to denote this graph by G prime. This is the graph obtained by adding this extra vertex Y with at least K neighbors in G. And the result says that G prime is K connected. Well, let us refer to this result as question 6. And the idea is to apply this repeatedly, starting with a base graph until we get the graph G with the required connectedness. To be precise, let us start with a complete graph on 4 vertices sitting inside the graph G. This is given by the red lines over here. Let me call this the graph G0, which is actually a complete graph on 4 vertices. Well, we know that a complete graph on 4 vertices has connectivity 3, which means G0 is a 3-connected graph. Let us write this here. The graph G0 is 3-connected because K4 has connectivity exactly 3, and so it is at least 3, and therefore the graph is 3-connected. We're going to apply question 6 by extending this graph G0 to a larger subgraph of G. And we will do this using the construction here given by question 6. So the idea is to add a new vertex to the graph G0 with at least 3 neighbors. Indeed, we're going to add a vertex with exactly 3 neighbors. So let's say we have this vertex given by the green dot, which has exactly 3 neighbors in G0. According to the result of question 6, the resulting graph will be 3-connected. Let us write this down here as follows. Since G0 is 3-connected, then the graph G1, which is constructed from G0 together with the extra vertex with exactly 3 neighbors in G0, is 3-connected. So this is just the result given by question 6. Next, we're going to extend G1 further to a larger graph using a similar construction. So let's go back to our original graph G and see how we can extend this further. Well, indeed, we can extend this by adding another vertex over here given by the blue dot with exactly 3 neighbors. Then the result of question 6 says that the resulting graph will be 3-connected again. You follow me? So formally we can write this over here, that these will imply the graph G2 obtained from G1 by adding a new vertex connected to 3 vertices in G1 is 3-connected. As before, this is the consequence of the result in question 6. Next, let's extend this further by adding another vertex. This time, let us choose this vertex here given by the purple dot with these 3 neighbors inside the graph G2. Let us call the resulting graph G3. So G3 is the graph G2 with this extra vertex over here and the 3 neighbors inside G2. As before, this is just the consequence of the result of question 6. And finally, by adding the last vertex, given by this black dot over here with 3 neighbors, the resulting graph, which is our original graph G, will be tree connected. Okay, so finally, as we expected, the graph G4, which happens to be our original graph G, obtained by adding this last vertex with 3 neighbors in G3, is tree connected. Again, this follows from question 6. Therefore, we have proved that the graph G is tree connected. Well, that means the connectivity of the graph G is at least 3. Now, to show the connectivity is at most 3, we are going to exhibit a vertex cut of size 3. Well, this is given by the following choice of 3 vertices. Let us call this vertex here A, and then the middle vertex here B, and this vertex here C. Clearly, the set U consisting of A, B, C is a vertex cut of G, because by deleting U, this black dot will get isolated, and hence the graph will be disconnected. So U is a vertex cut of the graph G. This implies the connectivity of G is at most the size of U, which is 3. Hence, it follows that the connectivity of the graph G is exactly 3. And we are done. All right.